invited to give this talk. Okay, and now it's recorded, I think. And there's new joiners. Let them get in. So what I would like to present about today is a topic we are concerned with for quite a while now. And this is focusing around the energy transition and also the role of geoscience and subsurface engineering within the energy transition. I mean, of course, it is a topic of concern because we all need to go towards net zero carbon emission, or in German would be Klimaneutralität. Net zero is, of course, again a bit fancier than Klimaneutralität, but it is what it is. I think the world needs to decarbonize, and some of the key requirements to decarbonize is actually to have geoscientists and subsurface engineers educate to meet that demand. And this is more high-level overview that I would like to give to you. So obviously, I mean, we all know that CO2 emissions into the atmosphere are increasing quite significantly. And this little sketch shows you the fluctuations in CO2 concentrations in the atmosphere over the past couple of 100,000 of years. And of course, the steep increase in emissions that we are seeing over the past, say, 200 years or so, or 250. So, and if you look a bit at the geological history, then we see that that the last time the planet had CO2 concentrations of 300 to 400 ppm in the atmosphere was during the mid-Pliocene, which was 3 million years ago. And back then, the temperatures were about 2 to 3 degrees centigrade above pre-industrial temperatures, and sea levels were at least 15 to 25 meters higher. So that gives you a bit of an idea of what there is to expect. I think the global temperature has increased already by 1.1 degree, and we already see a rise in seawater levels of something around 25 centimeters, but that will accelerate the more the world is heating up. So there's a lot to do to reverse that, or to at least stay within the goals of the Paris Agreement, which is a maximum temperature increase of 1.5 to 2 degrees. This is also something we clearly see in some of the key data. So this little sketch shows you the temperature changes around the world from about 1900 to 2018 across the different continents. The second from the top is Europe. So, and you see that Europe and Asia and Middle East got hit probably hardest. So we see the highest temperature increases in this part of the world, with probably temperature increases at least for the last couple of years of well above the global average of 1.1 degrees, so more towards 1.5 degrees already. But of course, we need to see that as a global problem and not as a problem that is seen by individual continents. So obviously, with higher temperatures, some parts of the world will become drier. This is actually not a part that got drier. This has been dry for quite a while. This is Salt Lake in Namibia. Been there a while ago during my master's. And of course, on the other hand, we see sea level rises. This is also not an actual sea level rise. This is just a high tide, North Berwick in Scotland. And this is my bravest PhD student, Georgi, who went into the water at, I don't know, it's probably only like 8 or 10 degrees. I would have never done that. Way too risky. And of course, all these weather extremes that we see all around the world, and the way we are exploiting our planet is triggering protest all around. And this is an example of the demonstrations related to the Hambach Forest. Most of you will have heard about that. So it has been in the news and media and all over the place, maybe 1.5 years ago, just before the pandemic. And the Hambach Forest is was meant to be mined or basically cut down for lignite mining, just between Cologne and Aachen, so not very far from where I'm at the moment. And on that particular day, which is quite interesting side story, I remember there was mid or end of October and it was 30 degrees outside, which is typically not the temperature you would expect mid of or end of October. And we went there to also show sign of our protest, basically. And there were 50,000 people in the middle of nowhere. So that gives a bit of an indication of how severe it is and what the public is thinking about it. And you might think that the majority of the 50,000 people were actually more like younger folks, like most you guys. But in fact, of course, those that are lifting the signs into the air were the more younger ones. But then you saw a lot of people, 40 plus, 60 plus, sitting a little bit on the side with cake and coffee, but also being there and protesting against the cut down of this Hambach forest. So these are typically not the pictures you see in the media, but these people were equally there. And it's not only the younger generation who dislike the way we are exploiting nature at the moment, it's also the older generation. And that is very encouraging, I think. So, I mean, with that, of course, it is global climate change is also changing the public perception. I remember when I started doing my PhD, like you guys are doing now, it was 20 years ago. No one cared about global climate change. So when we were doing the first kind of projects on CO2 storage, that there was an outcry in the media among the NGOs, like what kind of crap are you doing? And it's all coming back to the surface as a big bubble, and we're all going to die. That's of course complete nonsense, as we know today. And I think the opinion of the public has changed drastically. So universities are decarbonizing, communities are decarbonizing. Obviously, there is Fridays for Future movement. It's probably one of the biggest or the biggest youth movement that is around for many years. There is some milder versions of protest. There is, of course, also some not so mild versions of protest, like Extinction Rebellion. And I'm showing this because I've been to that event at the Scottish Oil Club. I had to be there back in the days. It's not that I particularly liked to be there, but yeah, there was quite a big protest by Extinction Rebellion people that made it into the news. Obviously, when the public is moving, typically the government is also moving, right? I mean, they are basically following the crowd, and with that, there's basically, there's a race all around the planet on who's achieving net zero goals the earliest. So I think number one at the moment, we will see if Germany can achieve it or not, is Germany, because Germany wants to become net zero carbon, klimaneutral by 2045. The UK used to be ahead of the race by 2050, which is something they announced already a year ago, more than a year ago. Then after the governmental change in the US, Joe Biden is also making commitments of becoming net zero by 2050. And even China is feeling the pressure, not only by the world community, but also by their own people, that there is a need for big change in CO2 or other climate gases into the atmosphere. And China is making the plan of becoming net zero by 2060, so a little bit later than the rest. Obviously, when the public is against it, when the government is against it, this is then also the moment where the companies start moving. And you may remember that big companies, also one of the companies that I worked for, Shell, but also ExxonMobil and probably many others, they were still claiming only like maybe 10, 20 years ago that climate change is a hoax. But now they are making big commitments towards net zero. And I mean, if you follow the companies on something like LinkedIn or in the media, you see big announcement about big green projects pretty much on a daily or weekly basis for all the Totals and BPs and Chevrons and so on and so forth. And I think for them, obviously, oil and gas upstream basically is bringing in the money now at the moment. But I think all the companies have realized that they cannot continue the way they have seen their business model for the next couple of decades. So there is a transition even in the companies. I mean, for my former colleagues in Shell, I know that the only research department that is receiving increasing amounts of funds is the one that is actually working on the energy transition. All the other ones that are more into oil and gas, they are facing big funding cuts at the moment, and this is in times where the oil price is going up and is actually at relatively low, high levels again. So this is probably relatively important as a background, and if you have seen it a couple of days ago, the International Energy Agency has released a new report on the energy transition. And they are making forecasts of how the world will use energy in the next couple of decades, so basically between now and 2050. And a bit of a summary is given here. So what you see is that especially oil and natural gas will still increase in the amount of energy they are producing, and you nicely see, I mean, this is predictions. You see this little kink around 2020. Obviously, this is due to the pandemic. This is very difficult to forecast. This is something you don't know if it's going to happen or not. But what you also see is that that little kink is relatively small over a year or two, and it's pretty much back to normal probably already next year. And then there will be a steady, not a major increase until it's reaching a maximum. And this maximum in oil production is certainly related to more developing countries, Brazil, maybe China, maybe Indonesia, and other parts of the world where the oil and gas industry is still ramping up, while in countries like the UK, Germany, for instance, oil and gas production is continuously going down. And of course, we should never forget the boom in oil shale and shale gas production in North America and successively in other parts of the world like Argentina, Russia, and so on and so forth. So this will lead to an increase in oil and gas production. Production of coal will be decreasing over the next couple of decades, but obviously not massively, because still some of the biggest economies in the world, China, India, they're still relying on fossil fuels to feed the economy and to basically achieve the kind of wealth that we earned over the last 100 to 200 years. But anyways, at the same time, the prediction is that, and that is encouraging, is that renewables will go drastically up from maybe something like 60, 70 etajoule today to more than doubling in the next 30 years or so. And so does nuclear energy will increase a bit, and so on and so forth. So, I mean, the consequence of all this is that we will see a decrease in CO2 intensity all over the economies. But is that sufficient to actually get to net zero, you wonder? And I mean, the difficulty in all this is two things. The one difficulty is that the world population will increase until 2050 from something like close to 8 billion today to something like close to 10 billion in the next 30 years. So that is difficult, but even more difficult is, of course, to accommodate the increase in global gross domestic product. So that means that a lot of people will move from what the United Nations would call poor to middle class. And middle class means that people are getting a house, getting a car, need heating or air conditioning or whatever you need. and simply want to use a good life that is, however, consuming a lot of CO2, or is leading to a lot of additional CO2 emissions into the atmosphere. And this is a major challenge, of course. And I mean, if countries like China are developing further and building up their wealth, it's very difficult to explain to people that they should also invest money to not buy cars, but to lower their CO2 footprint. I mean, this is of course possible in countries like Germany or the UK, but in many parts of the world it actually is not. So this leads to mechanisms to actually reduce CO2 emissions. And this chart looks a little bit complicated, but it is actually not so complicated. So if we start on the left-hand side, where it says 2021 to 25, you see this gray, which says activity. This is the increase in CO2 emissions into the atmosphere we would expect because of the increase in world population, and also the increase in GDP at the end of the day. So more people moving into basically the middle class. So which means we need to accelerate our efforts to actually lower the CO2 emissions again. And this is what all the different colors means. So these are the different mechanisms by which we can reduce our CO2 emissions to the atmosphere. And I added this little dashed line to give you an idea of where we are at the moment. So at the moment, we are at about 35 billion tons of CO2 into the atmosphere on an annual basis. So on the main mechanisms are those that we are changing behavior. I sometimes really think that this is wishful thinking. I guess that when we are all out of the pandemic, everyone is jumping into an airplane again. That would be my guess, but I hope not. So it will really be a change in behavior. It will be a lot of efficiency increase in energy supply, in industry, in transport. But then, of course, with the things that will really make a change is electric vehicles, electrification in general, renewable energies, wind and solar, of course. Hydrogen economy will make a change, which can really drastically help to decarbonize air traffic, for instance. But then also other things like carbon capture, utilization, and storage. So you're taking the CO2 emissions from CO2 point sources and storing them in the deeper subsurface. Or utilization would mean we are injecting CO2 into maybe an oil and gas reservoir to increase the production rate. Of course, that is bad again for the atmosphere, but of course, we are also getting rid of the CO2. Right? So all these mechanisms in combination are supposed to help bringing the CO2 emissions down to basically something that is then net zero at the end of the day by 2050. So that also means we definitely need the energy transition, and we also need a massive shift by a rapid growth in renewable energies. We need to dramatically increase the energy efficiency. And we especially need to decarbonize the energy industry. And the energy industry is probably still, not sure if it's the biggest industry there is in the world, but if you look at the turnaround of energy companies, then you would probably find 6 to 7 out of the 10 biggest companies in the world are actually energy companies, not in terms of profit, but in terms of turnaround. I think the turnaround of a company like Shell or Exxon is on the order of 300 billion every year. This is way more than companies like Google or Apple. Net profit is way lower, of course. So that also means we need a modified oil and gas energy sector, and that is leading to very large and long-term investment projects. And that is, of course, the advantage of having companies of the size of Shell or BP and these sort of things. They are used to dealing with very large projects on the order of 5 or 10 or even 15 billion per project. If you leave that to the governments, then you see what's happening at the airport relatively near you, right? It's simply ending up in a mess because governments aren't used to running such big projects. Energy companies are, and they're used to running them at cost and not at double cost, like you're seeing at the Brandenburg airport, for instance. The energy sector can do CO2 management and can, of course, also reduce CO2 emissions by storing it in the deeper subsurface at industrial scale. And this is what is happening at the moment. You almost see on a monthly basis at the moment that there's big new CCS projects announced by companies, typically in a consortium. And of course, these companies or the oil and gas energy sector, they have subsurface research management skills that we need. But what we also need is public-private partnerships. That's very important, and societal and political engagement to find proper solutions. So what does that cost? Quite interesting. Their report is already 2 years old, I think. Probably numbers have adjusted a bit. Quickly let Robert Neumeister in. So the estimate of a Morgan Stanley report is that we need an investment of $50 trillion between now and 2050. So that's $50,000 billion, or it's about 50 times what Apple is worth on the stock exchange, roundabout, maybe 40 times. So it's actually not that much, but it is, of course, a very, very, very big number. And most of the investments would go into renewable energies, as you can imagine, but also electrification of transport. And the majority is supposed to go into hydrogen. So it's not so much the production of hydrogen, but it's more like a distribution of hydrogen. Because if we want to use hydrogen as a source of heating, for instance, we need to adapt our natural gas grid. So all the pipelines need to be made hydrogen tight. And that is an investment, I think only for Germany would be on the order of 400 billion euros investment to turn our natural gas grid into a grid that can accommodate hydrogen. Biofuels to a smaller part, and then also carbon capture and storage is specifically highlighted in that report of 5% out of the 50 trillion, which makes it $2.5 trillion. So 2,500 billion investment into carbon capture and storage. And I sometimes really wonder if that is sufficient, but I think it's the right ballpark number. So
Professor,
let's have a...
I'll plus 5 as you asked.
Okay, yeah, that's perfect. Well, I need to hurry up a little, I guess. So that brings me a little bit to the sort of topics that might be important for geoscience and subsurface engineering. So where are we needed to actually work on the energy transition? This is shown in this very nice sketch that is done by one of my PhD students that I now use pretty much in every talk because it's a really nice sketch. So some of the main topics, and I mentioned geological CO2 storage before, is something you can see here. So we are taking CO2 from industrial point sources, for instance, and we are pumping it along pipelines. This is an onshore example, and then inject it into a deeper formation, maybe a saline aquifer that is overlying by a sealing unit. When we are moving towards a hydrogen economy, then the subsurface facilities will have difficulties of storing all the hydrogen. So like we are doing with natural gas for many decades already in Germany and other parts of the world, that energy source can temporarily be stored in the deeper subsurface, of course, at different time scales. So we can, for instance, get an excess hydrogen production from renewable energies during the night where we are consuming less. And then we might need to bring it back to the surface during the day when we need it for heating, for instance. Natural gas is more like done on an annual basis. So we are filling the natural gas reservoirs more in summertime, and we're producing it back more in winter time when we need the natural gas for heating. So this will be a major challenge, and there's ongoing activities in many parts of the world to look into the feasibility of using the deeper subsurface. There's also, of course, geothermal energy. I think something that especially the Geoscience is very active at is looking at low enthalpy geothermal reservoirs. So you can do geothermal, you can use geothermal heat at a depth of maybe only like 50 or 100 meter. So I think my brother has a house in Berlin with low enthalpy geothermal thingy in the cellar, and it's you know it's sufficient to get an increase in temperature of a degree or two, and with a heat exchanger, it allows them to lower their heating bill by, I don't know, 30 or 40% or something. So this is something that can be done at small scale, but you can also go big scale, of course, and do enhanced geothermal by drilling like really, really deep wells. And the most extreme one, I'll show you a picture in a minute, is what people do in Iceland when they're drilling into the upper mantle to get temperatures of a couple of 100 degrees. So let's have a look at geothermal energy. And this map shows you the kind of likelihood of where you could expect geothermal or extremely or relatively high heat flows when drilling into the deeper subsurface. So the darker the colors, the higher the likelihood. And you see Iceland as a good example. It's pretty much very close to the upper mantle. Mid-Europe, everything around the Alpine orogeny has a high potential. The Upper Rhine Graben, for instance, very big, or areas that are tectonically very active, like Southeast Asia. There's a lot happening here in terms of geothermal energy around Japan, on East Asia, or also the western side of North America, and so on and so forth, or the East African Rift Valley, just around here. So there's many places in the world, and probably not all of them have been mapped yet, but there's many places in the world where geothermal energy can actually be produced. And how does that work? Different ways. I mentioned a few examples before. A few examples that we are working on at the moment is, for instance, the United Downs project. So this is the deepest onshore drilling operation in the UK ever. And it's happening in Cornwall. This is in the south of England. If you've never been, please go and visit. It's really a beautiful part of Europe, Cornwall, really, really pretty. Much of Cornwall is just granite, and there's a lot of strike slip faults with relatively high geothermal gradients. And the idea here is to use these fault zones as basically a transport pathways to circulate fluids. So what the company did that is running the United Downs project is drilling 2 wells, one down to about 2.5 kilometers and one down to about 5 kilometers. 5 kilometers, we have about 190 degrees centigrade. So water is injected in the shallower wells and then pushed down towards the deeper well. And on the way, there's 2.5 kilometers in between. It probably takes a couple of months for water droplet to get from 2.5 to 5 kilometers. The water is expected to heat up to about 190 degrees before it's produced back. And this is supposed to produce electricity for more than 10,000 homes in that area. Even higher energy is produced in Iceland, as I mentioned before. So I think Iceland is close to being net zero already, but of course they have a easier geology, so they only need to drill maybe 1 kilometer or maybe 2 kilometers deep, and they're basically at the top of the upper mantle. So and there the main difficulty is really the technology they use for drilling that can withstand the very high temperatures. And there's a couple of operations where then energy is produced from the upper mantle. Something lower temperatures, something we are working on is using former mines. So can be a coal mine, can be any sort of mine where you have increased flow rates. And these facilities, depending how deep they are, between Glasgow and Scotland, they're usually only like 300, 400, 500 meters deep. The German coal mines, at least hardcore mines, are typically much deeper. And you can use these facilities to heat up waters by a couple of degrees, or you can even use it to store heat, maybe put it in summer and produce it back in winter, things like that. So this is considered as one of the really the bigger options to get to net zero within Scotland. So while all this is possible, we also need to face that geothermal energy is still niche all around the world. And this is what this figure is supposed to show. So if, for instance, the global electricity generation all around the world is on the order of 25,000 terawatt hours, geothermal are only producing about 100 terawatt hours, which is, I think, something like 0.4%, something like that. So really, really, really small amount only. And there's still, even though the numbers are growing, there's still a huge potential over the next couple of years. Another topic of high potential is hydrogen. Hydrogen can of course be seen as one of the cleanest energy sources there is if it's available. And hydrogen can be produced in many different ways. What is done today is typically brown to gray hydrogen, which means we are using fossil fuels to produce hydrogen. So brown would then be maybe a gasification of coal, for instance. And gray would be a refining process by which natural gas is transferred into hydrogen. Both options co-produce CO2. So if we are emitting the CO2 into the atmosphere, we are not winning anything. So the only way of making that entire thing green is to actually strip off the CO2 and injecting the CO2 into deeper subsurface. And this would then be a blue hydrogen. So this is hydrogen production plus CCS, or we even start producing green hydrogen, and this is the classical electrolysis that probably most of you got explained in your undergrads or in school times. Is splitting up water, right, into oxygen and hydrogen, and this is the cleanest version. It just is not very energy efficient, and it is quite expensive to produce green hydrogen. So the solution for that could be solar energy, maybe on the Arabian Peninsula and the north of Africa, wherever you're close to the sea, so you can use solar energy to maybe desalinate water and do electrolysis of the water to produce the hydrogen, and can sell that to Europe. I think this is what is considered in general, that while Europe was, let's take Germany, is actually a net importer of energy, but only in the form of natural gas. The idea is that in the future, we will still be a net importer of natural gas, but the natural gas will then be hydrogen and will not come from Russia or Norway, but it might come from North Africa or the Middle East, for instance. So why is hydrogen relevant for geoscience and subsurface engineering? Simply because the hydrogen needs to be stored somewhere. When we have excess production of hydrogen, like we are doing with natural gas already. And this figure shows you the storage capacity in gigawatt hours as a function of discharge time. So natural gas, as I mentioned before, this is the discharge time is typically on a biannual basis. So we put it in summer, we produce it back in winter. We can do similar things with heat, day-night cycles, maybe seasonal cycles, things like that. But we can also do that with hydrogen on a daily cycle at a relatively high storage capacity. So there is a lot of capacity in the deeper subsurface. And there has been a very recent, if you guys are interested, there has been a very recent kind of overview paper published by by Heinemann from Edinburgh University, also with colleagues at GFZ, who looked at the feasibility of subsurface hydrogen storage and how that could work and what the difficulties are. So the thing and the problem is a bit that hydrogen is, of course, a very small molecule, and the diffusion rates are relatively large. And we still do not fully understand, because there is no data on, PVT behavior, on relative permeability. So all basically the reservoir engineering parameters that we need to basically model the hydrogen behavior in the deeper subsurface. But that paper would give a very good overview. Hydrogen today, as I mentioned, is mainly brown to gray hydrogen, and this is also why today the low carbon share of hydrogen is relatively small, as you can see in that green dot. And the idea would be that the low carbon share, so that's really going towards green hydrogen or even blue hydrogen, would go to close to 100% by 2050, which means that by 2050, we wouldn't produce hydrogen from coal or oil or natural gas anymore, but really only electrolysis. A lot of the hydrogen is also already used today mainly in refinery chemicals, but also as an addition in iron and steel, with the idea that hydrogen could form one of the main energy sources in the future when it comes to aviation, road transport. So we are not electrifying our cars, but we are equipping our cars with fuel cells. I think it's quite a big topic in Japan already. It's not such a big topic in Germany at the moment, but Germany is also quite a bit behind when it comes to electrification of their cars. So probably fuel cells need to wait a bit. Electricity generation in general. So there is no necessary need of using whatever natural gas-fired power plants to produce electricity. We can also do that with hydrogen. And of course, blending the hydrogen into the gas grid. That's what I mentioned before, that we're heating our homes not only with natural gas, but then also with hydrogen in the future. Third topic is subsurface storage of CO2, a big one that is already around for decades. I think Norway started the first project in 1996. CO2 enhanced oil recovery is done since the 70s already. So this is not a new technology, but it seems new because it suddenly reappears in the media again. There's different ways of storing CO2. Some have been discussed. For instance, storing CO2 in unminable coal seam. That's more like a niche option. The main methods that we use is actually either storing CO2 in saline aquifers. So this is hydrostatically pressurized aquifers that are not drinking water horizons, so they're typically a little bit deeper. And there is depleted oil and gas reservoirs that can be used for storing CO2. How does that work? So typically we have a reservoir that is overlain by an impermeable seal at a certain depth, maybe below 800-900 meters. That has a lot to do with the specific properties of CO2. We want that to be in a very dense phase, and below about 800-900 meters, CO2 is in a supercritical phase with very, very high densities. So if we're injecting CO2, like natural gas would do the same, it would start migrating to the crest of the anticline and would start accumulating. CO2 is quite soluble in water, as you know, from every Coke, beer, whatever your bottle you're opening. Shake it a bit and you will see that the CO2 is coming out. So which also means it likes to dissolve in water. When it dissolves in water, it's forming a carbonic acid, relatively weak. But if the carbonic acid starts reacting with the rock, it might either dissolve or it might form carbonate. I think these are the carbonate cliffs from Dover, yeah, so south coast of England, which is a way of permanently immobilizing CO2. And whatever is not dissolved or not turned into carbonate would then exist as a gas phase within the reservoir, so either as a connected phase, it's what we call structural trapping, it's something that would happen at the top of the anticline, or it would be residual trapping, that means we have small little CO2 bubbles that sit within the pore space surrounded by water, so it makes them also immovable pretty much. Well, there's a lot of potential for storing CO2 all over the world. And doesn't matter if that is onshore or offshore. So of course we need very fixed sedimentary accumulations offshore to find the right CO2 storage location. But in general, wherever you find oil and gas is also places where you would find potential storage locations for CO2. Many of them in the North Sea, which is probably the closest to where we are at the moment. And this is also where the main activity is actually taking place at the moment within Europe, is the North Sea. Let it be the UK, Norwegian or Dutch North Sea. As far as I know, there's no activity in Germany at the moment to run their own project within basically German North Sea territory. Let me skip these two things. I think I'm pretty much running out of time a bit. And let me get to this one to give you an idea of where CO2 storage projects at the moment take place. There is quite a few of them. So it looks like there's plenty and they're all over the place, at least within North America, Europe, and Asia and Australia. Many of these projects are still in the development phase. So the development phase of a CCS project is maybe on the order of at least 5 years, depending on where it is. So the big red dots are those that are operational already. So in Europe, we have Northern Lights, Sleipner, and this dot is probably supposed to be Peterhead project, which actually didn't happen. That there was supposed to be a Shell project. There's this is the biggest one in Australia. This is the Gorgon project, operated by Chevron. Saudi Aramco is making some efforts over here, and of course the majority of projects are happening in the US and some of them in Canada. So there is activity all over the place. There is a lot of, new projects getting into the funnel, and might become live in 5 to 10 years time. And this is exactly what we need, simply because at the moment, if you're looking at the amount of CO2 projects, I think it's on the order of 40, and cumulatively these 40 projects are storing around about 35 million tons of CO2 on an annual basis. Right? At the same time, we are emitting by a factor 1,700 more CO2 into the atmosphere. So, and that gives you a bit of an idea on the amount of CO2 storage projects that we need in the next couple of years. So we need to ramp that up by maybe a factor of 100 or 200 or 300. So a lot of activities that would then take place. In terms of capacity, there's plenty. This capacity is in million tons. So in the US alone, we have the capacity of 205 billion tons of CO2 storage. Norway, UK, and Europe together will probably make it on the order of 25 billion tons of CO2 that could be stored there. So these are massive amounts, and this is only the part that has actually been mapped already. So there will probably be much, much more in reality. And this is important to keep in mind what the potential of CO2 storage is in the next couple of years. This is also how the International Energy Agency sees it. So the International Energy Agency sees carbon capture, utilization, and storage as one of the main mechanisms to reduce the carbon footprint of the cement industry. Fossil power plants, so that could be coal, gas, oil-fired power plants, but also steel plants, This is where carbon capture and storage could come in. And then we have DACS, which is direct air capture and storage, which means we are directly capturing the air out, the CO2 out of the atmosphere, collecting it, purifying it, pressurizing it, and storing it in the deeper subsurface. So the potential of that is big, and it seems like also that the International Energy Agency is seeing this as a key technology to really decarbonize the atmosphere in the future. So finally, let's get a little bit back into the role of geoscience and engineering in the energy transition. I told you that at the moment we are storing on the order of 40 million tons of CO2 per year. The IPCC report is predicting that we need more numbers on the order of 5,600 million tons of CO2 per year. So ramping up that by a factor of 100, 150 or something. And if you imagine that today 25, maybe 30 CCS projects that are in operation or production, they employ hundreds of engineers and geoscientists. If you imagine that that is ramped up by a factor of 100 to 150 over the next 30 years, that gives you numbers on the order of 10,000s of subsurface experts that are required to meet that demand. So I certainly wouldn't be worried about the longer term job perspectives in this area or in this area of application. And likewise, and I think this is also really going to change. This is typically a chart we are showing to our petroleum engineers, and many of our students are actually coming for petroleum engineering degrees. So typically, the number of petroleum engineers that are hired by the business typically relate to the oil price. So of course, if the oil price goes up, there's a higher demand, which means that more and more petroleum engineers are needed to meet that demand. And you could see the big peak in engineers enrolling companies in the 80s. You could see the same peaks only about 4 to 5 years ago, when the oil price was relatively high, reaching values up to $100 a barrel. At the moment, we are at lower levels in terms of oil price, but if you look at the oil price more, historically, then the numbers, I think it's at the moment something like $67 a barrel Brent, is actually really high. And this is where oil and gas business is earning quite a lot of money. So I think in the future there is quite a demand for subsurface experts in the oil and gas companies. But I mean, that I could imagine that demand is also growing because of the need of people working on hydrogen, on CO2 storage. Geothermal energy is typically not so much the area where oil and gas companies would invest. This is more something for more smaller, specialized companies, because there is a difference in, producing oil or gas from porous sandstones compared to producing geothermal energies from granite. So this is a different topic, requires different skills in terms of drilling, reservoir engineering, and so on and so forth. This is also a bit how the International Energy Agency sees it. So there is a small decrease in the number of jobs related to the oil and gas and coal industry to be expected between now and 2030. But I mean, if you would have asked me, I would have expected that loss would be bigger. So, but that probably goes hand in hand with the increase in demand for these sort of fossil fuels in the future. And I'm not sure where the International Energy Agency sees jobs related to hydrogen, CCS, or geothermal sitting. Could imagine it sits somewhere partly around electricity. So you're producing electricity from geothermal, you're producing electricity potentially also from hydrogen. And this is, of course, a sector that is meant to grow drastically. It's meant to almost double in the next 10 years or so. So that will create a major demand. So at the end of the day, I think with what is ahead of us in terms of the energy transition, there is a big requirement for geoscientists and subsurface engineers. I mean, it doesn't matter if you're a geoscientist or a geophysics or well site geologist or geomechanicist, or if you're a drilling, reservoir or completions engineer, doesn't matter so much if that is for the oil and gas business or for more for topics related to the energy transition. It is the same skills, right? I mean, you still need to kind of predict the porosity from well logs, or you need to see what is your fracture gradient, or you need to do a proper diagenesis study of your carbonate reservoir to see where you have sweet spots for porosity permeability and these sort of things. So that demand is there. We are just in a transition. So it might take a little bit of time until that demand is becoming more visible, and also until the companies have changed a bit their mindset. But it is there, and it is there to come, pretty sure. So a bit of a summary, and apologies that it really took again a bit too long. So there is an urgent need for rapid decarbonization of the energy, the industry, and also the food supply. I think that a modified oil and gas industry has the skills and tools and dimensions that are needed to support that decarbonization. There are topics, energy-related topics like geothermal energy, hydrogen, CO2 storage. I haven't mentioned compressed air energy storage, and probably other things that are increasingly becoming important and that are really much needed to support the energy transition. And although CCS, I gave you the numbers, $2.5 trillion is really a large ticket item, the societal value is absolutely undeniable, and I think this is recognized. So, and all this requires an immense workforce from both geoscience and engineering. And with that, I skipped the last slide, rather show you a nice picture of the Scottish North Coast. If you can ever make it, it's fantastic geology and it's fantastic colors. It's very pretty. So thank you very much again for inviting me and listening to this talk.
Thank you very much for your talk. It was really, really interesting. We haven't had any questions in the chat yet. Please, everyone, write your questions in the chat, or if you wish to ask your question in person, that's also possible. Then please raise your hand. While we wait for questions to come in, well, we can still ask a few questions for the last minutes. I see that Professor Muti already has a question, so I will ask her to unmute. Are you possible to, is it, Maria, are you able to unmute yourself and ask your question? No?
Yes, now I am. Okay. I was able to. Okay, so first of all, I would like to thank you very much for this wonderful presentation and for the really super broad scope that you presented to this audience of students. It's really wonderful to have this. Thank you very much again for your willingness to come to this virtual first meeting of this group. But actually, since it's a group of students, I would like to ask you a question. I've seen actually you had a master's program outline there. I would like to ask you what, I mean, of course, there will be possibilities for geoscientists in the futures, maybe even more, probably a bit of a different set of combination of skill sets. And I wanted to ask you, what would be the combination of expertise that students, graduate students, is the ones actually are attending this group, should carry with them in the next decade?
That's an excellent question, because it allows me to go back to that slide that I had on our master's course.
Okay.
It's not so much meant, I mean, you're all postgraduate students already, so it's not so much meant to advertise for our master's course. It's fairly new, and did a lot of thinking around that, like how can we better educate our master's students to meet that demand. Mm-hmm. And for that, of course, we had a lot of internal discussions, but we also our institute has a very big advisory board, mm-hmm. and that advisory board are quite a lot of industry professionals. So their brain power went quite significantly into this master's course when we put it together. And I wrote that course 2 years ago, coming relatively fresh from industry, so knowing a little bit that demand. And of course, it is a little bit more technical than standard geoscience masters that's typically taught in Germany. It's a bit engineering focused, where we think the demand is. But then again, our first cohort of students, they're basically all geoscientists. So they weren't too afraid of taking a course that is a little bit more engineering focused, simply because they got quite a lot of additional mathematics courses, which they clearly needed. That's always a bit the problem with geoscientists, including myself. Mathematics skills are usually not the highest. So what we are trying to teach them is then, of course, giving an overview on reservoir engineering, so things like fluid mechanics, geomechanics, these sort of things. Classical reservoir characterization is, of course, porosity, permeability, grain size, diagenesis, all these sort of things. That's very classical geoscience. But then also teaching the applications in very much detail. So we're basically trying to teach the requirements with a focus on the application. So you can explain what relative permeabilities or capillary pressure curves are when you're discussing it immediately with regard to a CO2 storage project, rather than keeping that separated. Or if the modeling can be taught directly in combination with geothermal energy production, let that be from a granite-based fault zone or simply like a geothermal aquifer. And this is what we try to do quite a bit. But then, of course, reservoir geophysics needs to be in there. The monitoring is key. But then we also thought that the only geoscience engineering technical skills are good, but not sufficient. So we also included things like economy, policy, and risk assessment of these projects. Because at the end of the day, I mean, it's the economy that determines if a big geothermal power plant is coming live or not. Right, so that's something we thought is also key. So what was a bit difficult, we had to ask quite a lot of people external to Harvard to help teaching that a bit, because we are also not really having the skills everywhere. But sometimes, I mean, asking someone in industry to give a two hours talk about reservoir monitoring is sometimes more efficient than me putting that together myself and presenting it over 8 hours, right? Simply because people are the key expert and know what they're talking about. So that's a bit the thing. So yeah, I mean, I think students like it quite a lot.
So may you ask, so is it already starting? It's already you already have graduates from this program?
Yes, so the first students are graduating this summer.
Okay, wonderful. Okay.
Yeah.
I think I really admire how in the UK you're so flexible in adapting to the demands of the world, and somehow all these regulations. I mean, for example, I think about a German system, even trying to bring together geoscientists and geophysicists is sometimes problematic. To try to bring together geoscientists with engineers would be very difficult. I mean, think of all the schools, in Germany. There is a different, I really admire the pragmaticity and the vision that somehow you really have in the UK. You can carry these visions through. It's phenomenal.
No, absolutely. I like that too. I mean, that's of course a positive. And the negative is, of course, I mean, all master's courses in the UK is all business cases, right? I mean, the universities need to fund themselves through these master's courses, so there is a certain pressure. If we see numbers going down, then of course the head of school is coming up and saying, can't you start a new course that is bringing in more students?
I see. Okay.
Yeah, but other than that, it's relatively straightforward to come up with a new master's course and getting that through university and getting approval if you have a good case.
Okay, I would be curious to know if these people will be already finding employment after a master's. That sounds like a very, very demanding one to do in 1 year, for sure.
it is. I mean, I'm glad that I was given a little bit more time to do my diploma back then. Didn't do masters, I did the diploma, but of course, I mean, didn't do that in 1 year. So they're really working from the morning to the night, the entire year, and cost them quite a lot of money. Yeah.
So I would keep talking with you, but actually, I see that there are other questions. Maybe Thomas, I give you back the word and
Yeah,
let
sure.
you run the operation.
I see that Robert Neumeister from the Vrije Universiteit, one of our partners, also has a question. So I will ask him also to unmute and go ahead, Robert.
Yes, thank you, Thomas, and thank you again for this wonderful presentation. I really liked it. I have one more specific question about the hydrogen storage, because we have in the North German basin, we have quite a lot salt caverns there, and I was wondering, like right now, we're like almost storing there entirely or completely only oil and gas. My question would be: is it possible to store hydrogen there too? And a follow-up question would be: I think you mentioned it in your talk that you have to storage hydrogen on a daily basis, and maybe you could explain that a little bit more, because how is that working in this case? So, yeah, would salt caverns would be accessible for this?
Yeah, totally. I think the technology enabler for subsurface storage of hydrogen will be salt caverns. It simply is lowest risk, right? I mean, the problem with the salt caverns, I mean, that works very well for oil because oil comes at a relatively high density, right? But hydrogen has a density that is significantly lower than oil. So if you put it into weight, the mass of hydrogen you can put into a salt cavern is relatively low at the end of the day. And the salt caverns are quite limited in volume, right? So the porous reservoirs would give you much higher capacity. But that is, of course, also something that needs to ramp up. I mean, if you take the International Energy Agency and their forecast of that shows how important hydrogen will become in the future, then maybe within this decade, the salt caverns might be big enough, but then maybe in the next decades, they're not going to be big enough. And of course, salt caverns is something there is in the North European basin quite a lot, but when you don't find them in Scotland, you also do not find many of them in England or in other parts of the world. So it's a bit specific to the Permian basins, pretty much. So yeah, I mean, there is publications, there is reports that summarize the capacity for hydrogen storage and salt caverns, and this is clearly seen as an opportunity, also because I mentioned before that hydrogen is a small molecule, and there's always a risk of the hydrogen diffusing out of wherever you want to have it, and for that, salt is of course the best material. It's relatively leak diffusion tight, so it's quite optimal. Yeah. So sorry, what was your second question?
No, the first question was perfectly answered, and the second question would be, if I understood it correctly, you were saying that that you have to store the hydrogen on a daily basis. So does that mean that you have to import and export it out of the salt cavern on a daily basis, or what does that mean?
No, I mean, the idea is more like I mean, what we are doing at the moment with natural gas, or probably also with oil, is we are getting it through a very long pipeline from Russia or Norway or somewhere, right? So it's traveling already thousands of kilometers of distance. For hydrogen, this would rather be local solutions. So maybe you're having an offshore wind park in the North Sea, where you're producing the electricity that can help to split up water into hydrogen and oxygen. And maybe you can consume the hydrogen right away for whatever, but maybe you don't need the hydrogen, for instance, in the night where we are heating less. And then you could basically locally store the hydrogen, and that maybe even on a daily basis. might be weekly basis, but always depends a bit on the demand. I mean, it is a technology, or the combination of technology always has a bit the advantage of what do you do with overproduction of electricity from wind generation, right?
Yeah.
I mean, if the grid is full, what do you do with the additional electricity that is produced? And I think what a lot of the wind park companies are doing, they're basically turning their windmill out of the wind, that it stops producing electricity. And that way you could continue just converting the electricity or the energy into something else, and that could be hydrogen.
Perfect. I like this application very much, because I mean, we had it, I think, in the last couple of years, a lot of times that Germany was producing a lot of wind energy that they then had to transfer, for example, to Switzerland or so on, and had to even pay them to that they take our energy. Yeah, so that would be a perfect application for that. Thank you very much.
You're welcome. Thanks for the question.
Yeah, thank you, Robert. I had a question myself, actually, that I wanted to ask you. Is like the newly published report of the IEA. They also published this roadmap for how to go forward to 2050, and they actually suggested also that from 2021 there will be no oil and gas field developments approved, and so no more fields approved for development. And I saw on LinkedIn that this was a bit controversial, but I wanted to ask you, what's your take on that, and how do you see more broadly, like, the role of natural gas towards the future?
Yeah, I mean, this is of course what the Energy Agency is suggesting. What would need to be done to actually get to net zero by 2050 or something. This is of course not what is going to happen, right? I mean, I guess that Germany is not drilling new wells for oil and gas anymore, and the UK has also stopped giving out licenses for new field developments. But this is Germany and the UK. I mean, there's other parts of the world that actually require drilling for oil and gas to bring in the money to actually invest in technologies to decarbonize the industry, for instance, right? I mean, take Nigeria is probably a good example. I discussed it with I had a poster who came from Nigeria. We discussed it for really long. I mean, Indonesia has what, 200 million inhabitants at the moment, and is expected to grow to 600, 700 million in the next couple of decades. There's a lot of oil and gas in the Niger Delta. Of course, something needs to pay for infrastructure, for houses, for whatever, to accommodate this increase in population. And of course, then you also need to create a surplus in order to invest into green technologies, to invest into wind parks, to invest into solar panels on the roof, and maybe to give governmental subsidies like that is happening in Germany. So all that is needed, and for all this, the money needs to come from somewhere. And I mean, hydrocarbons have paid for most of the things in Europe and North America, and it will also pay for many of these things in emerging economies like Nigeria or Indonesia or wherever. So I think that needs to happen, and as such, I also think that oil and gas won't be gone from the global map in the next 10 or 20 years. It will stay, and the same with coal. Right? I mean, Indonesia is making an economic boost because they are more and more producing their coal reserves at the moment, and that's quite dirty because much of it is also surface mining, like we are doing in Germany, right? In the Lausitz or in the just here west of Cologne. I mean, it isn't pretty, and it's. But I mean, we also did it, so we cannot tell Indonesia not to do it. It's very difficult.
Actually, there is also a moral questioning, somehow, how can you tell other countries that actually they're not able to use their resource, it goes into another domain of discussion and somehow is out of our scope here.
No, very much. I think you asked about shale gas or natural gas and the boost. I mean, we have it as part of our MSc, as you can see, transitional gas, because it really is meant to transition from coal to renewable energies. And the more we are using natural gas to produce electricity, the less we can use coal to produce electricity. And natural gas is emitting only half the amount of CO2 into the atmosphere than coal for the same kind of energy output. So that makes quite a big difference. And I think also shale gas is there to stay for the next couple of years. I mean, it is a dirty technology, but I mean, I think there's huge reserves in Russia, there's huge reserves in Argentina, and Australia, and Australia isn't the greenest part of the world anyway. So I mean, they will all, make that available.
Okay, thank you for your answers. I think we went a bit over time, but I think that we will close here. Thank you to everyone that participated. And we hope to see you all again at our next lecture. Thank you very much again, Professor Busch. It was really a very amazing talk, and I think we all took away some insights for the future.
That's great. Yeah, thanks again for inviting me and the excellent questions. And I hope to see you soon at some point at Geoscience or Potsdam or Freie Uni Berlin, wherever.
Certainly.
Well, we hope to welcome you in person soon at the next possibilities. I'm pitching in for my students, so but I let them close the event.
So,
all right.
Thank you all for attending, and we want you to know that we have just dropped the link to our EAGE LinkedIn page. So we'd like you to just connect with us so that you can have the latest information about our future events. Thank you very much, and we hope to see ourselves again soon.
All right. Have a good evening.
Have a nice evening.
Thank you
Thank you so much.
Bye.
And
bye.
Thank you.